Okay, we can start. So this is the second lecture about TinyOS. We will see today how to simulate a TinyOS application. So we will look a little bit at the Tossim simulator, what are its functionalities. We will see another example of a TinyOS application. And then we will see how to, let's say, merge together all the tools we have seen so far by using by simulating a TinyOS application into Kuja and by connecting Kuja with Node-RED so that we get the data from the application in Node-RED. Okay, so this gives you a basic starting point for developing prototypes and testing applications. Before we start, any question on the previous topics, curiosities or troubles that you had with the virtual machine? Okay. Regarding the projects, I have started putting together a document, and I guess it will be ready by next week. Okay. So I'll send an email to everybody when the document will be online. Okay, good. So today we will move a little bit into the world of Tossim, which stands for TinyOS Simulator, and we will see why we need it and how to use it, basically. Let me just plug my power. Okay, so we have talked a little bit about this already in the previous lecture, but it should be clear now that when we talk about the wireless sensor network and in general for any application that regards the Internet of Things, we are generally talking about large-scale applications. So we envision application in which we do not have only one sensor, okay, but we have a, let's say, distributed scenario in which many sensors are collecting data and are delivering this data somewhere, okay. Generally, these sensors are placed in inaccessible places. So this is not true, let's say, 100% of the time, but there are particular classes of applications where these sensors are deployed in such a way that it is difficult to go there physically and check if there's a problem or to change something. I can give you a couple of examples of applications we have worked on. For example, think about parking lot monitoring sensor network where you have one sensor per parking spot, okay? And the sensor basically tells you whether there's a car or not in the parking spot, okay? So you would like to retrieve all this data and, for example, provide this information in real time to drivers in order for them to understand whether there's a space in the parking lot. Now, generally, these sensors are buried under the asphalt, okay? That means that you put the sensor and then you put the asphalt on top of that, okay? So it's difficult if there's a problem to replace these sensors, right? You have to go there, remove the asphalt, check the sensor, and remove the sensor. Another example that I already gave to you is all those applications that regards, for example, environmental monitoring, okay, like monitoring the temperature inside or the acceleration or the vibrations inside the mouth of a volcano, or again monitoring the vibrations on a bridge, okay. All those applications where sensors are placed in locations which are difficult to access, okay. And so in those scenarios, the physical layout, the physical network is generally deployed only once at the beginning of the lifetime of the application, and that's it. It's very costly to go there and move the sensors and find out whether there's a bug or not, and so on and so forth. So we have generally little room, also, both in terms of cost, time, and actually, effort to redeploy the sensor network on errors. And by redeploy, I mean both physically, so moving the sensor physically, or just by putting new software, new code on the sensor themselves. Okay. Also, if you keep the sensor where they are and you just have to reload the code, that could be very costly. Okay. And you do not want to do that, basically. Okay. Now, whenever we create an application, you should know this. You want to check that it works. Okay. So whenever you create something, software or hardware, whatever, once you have created, you generally test it in order to see whether it works according to the specifications or not. And well, when we talk about applications for sensor networks and in general for Internet of Things, which entails the hardware that we have seen, so this very low cost and low power hardware with, let's say, minimal computational capacities, then even testing that the application is working correctly might be very difficult. Okay, and generally because it's very hard to debug applications based on sensor networks. There are so many variables that you can't just try again the application until you find an error, okay, in real life. And if you look at what TinyOS authors, so basically the inventors of TinyOS, said about debugging application for TinyOS, well, you have to prepare for a painful experience. Okay. Just to give you two examples on why this experience is so painful. So imagine that you have prepared your application and you have loaded it onto a sensor, and then you want to understand whether it works or not. Okay. So in terms of output, well, you don't have much. Okay, you just have these three LEDs, yellow, red, and green or blue, depending on the sensor, that you can, let's say, trigger on and off to understand whether the sensor is doing what you want. Okay. Now with three LEDs, we can have up to 8 combinations. Okay, 2 to the third, 2 because on or off to the third, so 8 combinations. That means that we can somehow make our sensors tell us 8 different things. Okay, not many more. Second, when you test the behavior of a sensor in the real life, well, there are really many variables that you just can't simulate. Okay? So, for example, the radio environment, meaning how packets propagate through the air from one sensor to the other one. Well, that's difficult to simulate, okay? That's difficult to model. And you can have actually different behaviors that are very difficult to spot in real life. So, we would really like to have some sort of simulation scenario in which we can run our code before actually deploying it on a real sensor network with the purpose of spotting whether there are bugs or not in our implementation. Okay? So that's something that we really would like to have. And of course, by doing this, we have a lot of advantages, but we may also have disadvantages. Okay? So, for example, the advantages are that we may want to study our system in a controlled environment. By controlled, I mean that we can decide how many sensors are out there, what are the, for example, radio links, and how these radio links are characterized between the sensors, or we can, let's say, control parameters such as the transmission power of the sensors, the energy which is stored in the sensors, and so on and so forth. So we can test how the system behaves in a controlled environment. We can observe interactions which are difficult to capture live. For example, what happens when one packet is lost, or what happens when 10 hundreds consecutive packets are lost. And these situations may be difficult to achieve in real life. So we can, let's say, shape our simulation in order to behave exactly as we wish. And by doing this study, we can, of course, improve the system design, because, for example, we encounter a situation in which there's a bug, and so we can solve the bug by, for example, modifying the source code. That is something that is very difficult to see in real life, because when we encounter a problem in real life, we do not know the exact motivation of this problem. While if we encounter a problem in simulation, we know what are the parameters under which this problem was encountered, so we can try to reproduce the problem many times to see whether we can find a solution for that. Okay? Something that in real life may be difficult to achieve. And of course, this is a very, very cost-effective alternative to deploy our system in real life and testing it for maybe 1 year or so before actually spotting the problem. Okay? Of course, we can have some disadvantages if we try to simulate the application instead of running it in real life. What are these disadvantages? Well, first of all, the simulation may not represent the accurate real-world scenarios. Okay? So it's very difficult to simulate real life. Think about how the information propagates from one sensor to the other. That's basically radio communication involved, and radio communication is complicated to model. Okay? There are so many variables that affect the way a signal is transmitted and received between 2 points. And of course, all the, let's say, results that we get out of our simulation, well, they depend on the modeling assumptions. Okay? So, as long as our assumptions are close to the real life, then the results will be valid also in real life. But when the assumptions that we make are maybe too simple, okay, then the results that we obtain will not be useful for real life. So we may have, let's say, something which is not coherent with the proper operation when we actually deploy the sensor network in real life. Okay? And this is something that always happens with simulation. Okay? So if you want to have a simulation which is simple, you have to have simplistic assumptions which may differ too much from real life. Otherwise, if you want your simulation to match a real-life pattern, you have to make it very complex and it may be difficult to manage. Okay? So there's a trade-off between simulation complexity and validity of the results that we get out from the simulation. So what do we use for simulating a wireless sensor network or a wireless network in general? Well, luckily there are many tools out there, okay? So we don't have to worry too much. There are very standard tools used for evaluating networks in general and wireless network also, like NS2, NS3, ONNET, so on and so forth. The problem of these environments for simulations is that they are not very suitable to wireless sensor networks, mainly because they are either too fine-grained, so they go too much into the details of the simulation, or on the other side, they are too coarse. Okay, so they just give overall ideas on how your implementation is going. And generally, these environments do not address the complex interactions that we have in sensor networks. Okay? Both among modes, so when you deploy a distributed application composed by many sensors that we call modes, we have interaction between these modes, and we would like to have a tool that can capture these interactions, not only among modes, but also within a mode itself. Okay? So that, for example, gives us the access to the different stacks, or better, layers of the stack that we have installed on our mode. So we would like to have something that can give access to these two, let's say, interactions in a single environment. And that's why Tossim is generally used for simulating this kind of sensor networks. So Tossim is a discrete event simulator, meaning that it discretizes time, as many simulators do. The very good thing is that when you want to use Tossim, you don't have to spend a lot of time in converting the application that you have created in a programming language which is suitable for simulation. The good thing of Tossim is that you take your application and you use exactly the same source code that you have created for the simulation itself. Okay? So you don't need to modify anything, or we'll see that you just need to add very, very little instructions in order to make your code suitable for simulation. Okay? The good thing is that once you have spotted a problem, you solve the problem directly in the source code, and that modification will be valid also for the real development. Okay? So by simulating, you spot an error, you correct it, and that would be basically directly implementable in real life. So it's actually debugging an application. Now, the framework in which you debug those applications is generally a small source file. We will see it today, which can be written either in Python or in C++. But this is just how to launch the simulation, meaning how many nodes you want inside the simulation, and so on and so forth. The code that each mode will run is exactly the same TinyOS code that you will then load on the real hardware. Again, what are good features of Tossims, which are basically the requirements that we would like to have for any simulator of wireless sensor network? Well, we would like it to be very scalable, so to allow to test applications in which we have a lot of nodes, in the order of 1,000 nodes. We would like it to be complete, meaning that we would like it to cover as many interactions as possible between nodes and among layers of the stack on each node, in order to simulate complete applications. We would like it to be to capture real-world interactions. So what happens, for example, when the link between two nodes fails, okay, or when one node depletes its energy. So what happens to the application? Can it reveal unexpected behavior? So, for example, when we receive a packet with a particular value of the data payload, maybe our application cannot handle it. So what happens in that case? Can we reveal any particular bug in that case, and so on and so forth? And so these are all requirements that we would like to have for a simulator, and in fact, Tossim has all these requirements. So we have seen that the first one is scalability. So we would like to simulate applications by putting together many nodes. Partially, we have seen that also Kuja does that. If you remember, last time we have seen how to create a simulation in Kuja, and one of the first things we played with was the number of nodes to create in the simulation. Okay? Now Kuja allows you to do this by simply selecting how many nodes you want to create. Tossim more or less does the same thing. So actually the way that you specify how many nodes you want to use in Tossim is a little bit more advanced than the one that we have seen in Kuja, because in Tossim what you actually create is the network topology itself. And by network topology I mean how many nodes are there and how these nodes are connected to each other. Okay? So in Kuja we have seen that you can move nodes inside or outside each node's communication range. In Tossim, you have to specify a priori what is the network topology, meaning that what are the links that go from one node to another node, and we will see also what is the quality of each link. Okay? And that basically gives you a broad range of scenarios, like what happens when the link between two nodes is very good, what happens when it's very weak, and so on and so forth. We will see how to create, of course, a network topology. Just remind that the radio model that is used in Tossim is signal strength based, meaning that what you actually specify is what is the strength of a signal which is transmitted by one node and received by another node. Okay? So you can either specify if the strength is high, meaning that you have a good link, or if this strength is very low, meaning that you have a weak link. So generally, well, actually I would say always, in Tossim you specify this network topology in a plain text file, okay? And you actually specify links as lines in this text file, okay? So, for example, one link in the network topology is defined by a triplet of number, for example, 1 to minus 54, where the first two numbers are the identifier of the nodes in the network, okay? And the third number identifies the channel gain between the two nodes, okay? In dBm, so in decibel milliwatts. So that line, 1 to minus 54, it means that there's a link between node 1 and node 2, and the received signal strength between node 1 and node 2 is minus 54 decibel milliwatts, okay? Which is actually a good value. Okay? Generally, values from minus 40 to minus 70 are considered good values for a link. Values below minus 70, meaning minus 80, minus 90, are considered weak values for a link. Okay? So you can divide, let's say, a link in these two categories, good link or bad link, depending on the value that you put on the line corresponding to the link. And note that links can also be asymmetric. Okay? So you can specify another line in the topology text file where instead of having 1, 2, you have 2, 1, meaning that the perceived quality of the link is different with respect to the direction you are looking at. Okay? Whether if you're transmitting from 1 and receiving at 2, or transmitting at 2 and receiving at 1. We will see examples, of course. Then when you basically set up a simulation, you have to specify a noise trace, it's called noise trace to the simulator. The noise trace basically simulates what is the effect of external noise on the links of your topology. So basically, you can decide what kind of noise to introduce in your simulation. Okay? You can either introduce no noise, meaning that all links will have the gains that you have specified in the topology, or you can decide to introduce some noise in the simulation so that your simulation will have at runtime a different behavior depending on the, let's say, time at which you are in the simulation. And what is actually done, you feed the simulation a noise, which is a trace like this, okay, with some spike of noise here and there. And whenever a packet is received in your simulation, you evaluate the current value of noise that you have in this trace, and you compare it with the channel gain that you have set on your link. Okay? Now, if the channel gain on the link is higher than the, let's say, interference value in this case, then the corresponding packet will be received, otherwise you will have an error. And this basically simulates the way a packet may be lost on wireless link, depending on the noise that you feed in the simulation and the value that you have specified for the goodness of the link. Okay? So by changing the two values, you can simulate many applications, many scenarios. Scenarios where the link are very good but the noise is high, scenarios where the link are weak but the noise is low, and all the combinations in between. Okay? And that gives you a starting point for evaluating your applications in many different scenarios. Okay? And basically, to assess that your simulation is, your application is working fine, regardless of what radio environment you will find in reality. Okay? Actually, a good starting a good simulation strategy for this is to test your application in all the possible scenarios, to see what happens when a packet is lost, when many packets are lost, when no packet is lost, and so on and so forth. Okay. Any questions so far? Now, we have basically understood now that one of the main limitations of TinyOS is that when you move to real hardware, you have no proper means of outputting information. Okay? We have seen that we have these LEDs, but apart from those, we have no actual ways to inform the user of the application of what's happening, right? Now, luckily, when we simulate, we can actually output text. Since we are simulating, so we have no real hardware, but it's actually a software which is running in our PC, then we can also output some statements, so some text, to understand what the application is actually doing. Okay? And in particular, there are three instructions that we can insert in the TinyOS code, and we will see in a while how are they used. And the most important one is the DBG instruction, which, as you can imagine, is basically the equivalent of a print statement. So it allows us to print text on the output terminal. So this function accepts two parameters. The first one is the debug channel, and the second one is the actual text that we want to print. Now, the first parameter, the debug channel, can be either the output terminal or, for example, a text file, and you can specify as many debug channels as you want. Okay? Why do we want to separate debug statements? Well, it might be useful when, for example, you have very complex application, which we have, for example, the radio stack, which is doing something. On top of that, you have some processing functionalities that are doing something, and you want to check if the two separate blocks are working fine. So you may have one debug channel just for the radio stack, for example, and one debug channel just for the processing functionalities. So that if you spot an error in one of the two blocks, you can just focus on the debug statements which were written on the proper channel. Okay? So this is generally done for simplifying the life of a debugger. Okay? Of course, you can also decide to put everything on a single channel, and then it's up to you to understand where the problem was actually. Well, and then there are other, let's say, instructions such as this one, which clear everything, and dbg error, which is similar to this one. It just outputs something like this. So your text, but before it an error. Okay. So you may decide to use this or this, depending on whether you just want to inform the debugger of something, or if you end up in a situation where an error is. Okay. So when you want to compile an application for simulation, again, it's very similar to compile it for the real-world case. You just have to add the keyword sim at the end of the command. Okay. So we have seen last time for TinyOS B hardware, we use the keyword make TinyOS B. When you want to simulate, what Tossim lets you do is just simulate for Mica Z platforms. So what you have to do is basically to write make Mica Z sim, and this will create an executable starting from the source code that you have created, which then can be simulated. We will now take a look at a very specific application and how to simulate it, and we will run the application. Everything is on your virtual machine, so you can also follow me while I do this. Okay? So the application is the following. We will create a TinyOS application with two nodes, basically. The first node transmits a request message to the second node. Upon reception, sorry, let me rephrase it again. So we have two nodes, and we would like to exchange some data between these two nodes. Okay. So the first one will try to contact the second node, and in order to be sure that this request message was correctly received, we will ask for an acknowledgement to be received by the transmitter. Okay. Are you familiar with the concept of acknowledgements, right? So we will do this, and we will simulate the fact that when the first request message is transmitted, the receiver is actually in an off state, so cannot receive any message. Since it cannot receive any message, it cannot transmit the acknowledgement back. Okay? And the first node will understand that no acknowledgement is received, so it will retransmit the request again. This time the request will be correctly received, so an acknowledgement will come back. That's good. And the receiving node will also transmit a response message, and in the response message will be contained some random data which will be retrieved by performing a sensor reading. Okay? So imagine that the second sensor contains some sort of temperature or humidity sensor, and we will actually trigger the acquisition of a measure from these sensors, put the value into a packet, and transmit it back to the first node. At this point, having received the response, the first node will send an acknowledgement back to the second node. Okay. So we will go very, very quickly into the TinyOS code that implements this situation, and then we will see how we can simulate it. Okay. So if you go into your virtual machine, there's a folder here on the desktop, IoT examples. I have to be. There's a folder TinyOS here, and another folder which is called SendAC. So you can open basically two files here, SendAC C and SendAC app C, which are the configuration and the implementation, basically. So let's start with SendAC C, which contains the actual implementation, so the code of this application. If you remember from the last time, in the first part we have to specify what are the interfaces that will be used for this application, and we have seen that the boot interface is already there. Sorry, it's always there, and it's basically the starting point of any TinyOS application. And then we have to specify all other interfaces that we want to use. Now, if you think about the application, it's basically communication between two nodes, okay? So what we need is basically all the interfaces that we have seen for communications, so active message packet. In this case, we will use acknowledgement, so we will use a new interface which is called packet acknowledgements. Then we have active message send, the split control, which is the interface used to turn on the radio, the receive interface, which is used to receive messages. Then we will use a timer, we will see why. And then we have also a new interface, which is the read interface, which is generally used to perform sensor reading. Okay, so we will use this interface to get the value from a sensor, and then we will use this value to fill the packet that we want to transmit to a node. Let's look at the implementation. So in order to look at the starting point, I need to go to the boot.boot event, which I remind you is the event which is triggered by the operating system when everything is ready to be run. Okay, so this is basically the starting point of our application, and what I'm doing here, I'm printing a debug statement, okay, on the channel boot. We will see then how to specify this channel, but what we are writing here is that the application is boot. Okay, so this will be the first statement that we will see out of the simulation. What we will do is to start the split control. So the first thing that we do is to start the radio, to turn on the radio. Now, why the radio is not already started? Well, because the radio chip is basically the component of a sensor node which consumes most energy. So it's good to keep it off and turn it on only when you need it in order to save energy. Okay? So that's why when you start a TinyOS application, the radio is by default in an off state, and if you want to use it, you have to turn it on. Now remember that when you call start, you generally have an event which is coming back, which informs you whether this starting was successful or not. And in this case is the start done event, where you can check if the start of the radio was successful or not. If was successful, then we will print with this debug statement that the radio was correctly turned on. And look, here we are using a different debug channel as before. Okay, first we were using the boot channel, now we are using the radio channel. We will see again why this can be useful. Now, in TinyOS, we actually need to specify what different nodes may be doing. Okay. Think about Kuja, what we have seen last time. If you remember, and we will also see today again, for each node in the simulation, you could specify what was the executable, so the actual code that the node should run. Okay. In TinyOS, it's not like this, it's a little bit different. So the simulations that you can set up are basically constrained to run the same source code. So all nodes in a simulation will run the same source code. That means that if you want different sensors to do different stuff, you have to specify it directly in the source code. Okay? So for example, here, if you remember the application that we are going to write, we have two nodes, and we have node 1 that transmit a request to node 2. Okay? So what we want to specify here is that if the node which is executing the code is node 1, it should transmit a request. Okay? And in fact, that's what we are writing here. We check the value of this variable, toss node ID, which is a variable that stores the identifier of the node, and the identifier is the address of the node, basically, the physical address of the node. And if in this situation node 1 is executing the code, then we will write, I'm node 1, I will start sending periodical requests, and we will start a periodic timer. Okay, so we would like actually to transmit these requests periodically, not just once. Okay, if you want to transmit it just one, we can start a timer which is one shot, not periodic. Okay, so start one shot instead of start periodic, but this is just a detail. Okay, so we have started this timer. We will wait for events coming from the timer. Okay, so whenever the timer fires, if you remember, we have an event that comes back from the operating system. Let's find it in the code. Here it is. So whenever the timer fires, what we will do is to call this function, which is actually a task. If you remember from the previous lecture, we have seen what is the difference between tasks and functions. Okay, let's say you don't actually have to understand it now, just assume that this is a proper function. Okay, so it's something that is executed by the scheduler. Let's just find what it does. It's probably here. Okay, this one. So whenever this function is executed, I will prepare a message, and let's see how this message is specified. So let's open the header file for this program, which is this one, sendarc.h. In this file, you have the specification of the payload of messages which are exchanged between the two nodes, basically. So between the two nodes, we will have messages which contains 3 fields. The first field is the message type, which can be a request or a response. The second field is message ID, and the third field is the value which is inside the message. Okay. Now, this is the way in which you specify the structure of a message in TinyOS. So it's basically a structure of fields, and you can specify whatever you want inside this field. So if you need a message with 10 fields or 20 fields, you will have to specify all these fields inside the structure. And you can then access each one of these fields and modify it with the data you want. So here, basically, you specify what is the structure of the message. So we have message type, message ID, and message value. And whenever the timer expires, we will put into message type, we will basically specify that the message type is a request message, and the message ID for us is basically a counter that goes on and on. So it's basically a sequence number of a message. The first message will have ID 1, the second ID 2, 3, 4, and so on and so forth. Okay. So once we have prepared the message, we can, for example, write something on the debug channel. We can say, okay, I'm trying to send a request to node 2 at a specific time in the simulation. Then this is a command that you can call on the packet acknowledgement interface to actually inform the receiving node that the packet received must be acknowledged. Okay. So this basically set a flag into the message informing the receiver that the message has to be acknowledged. And at this point you can transmit the message. So you can call the amsend.send function. If you remember, the first parameter of this function is the destination address of the message. Last time we have seen broadcast addresses for destination. This time we will use a unicast address. So we will specify that this message is to be transmitted only to node 2 in this case. Okay? So we will transmit our packet to node 2. And if this transmission is successful, then we can write a bunch of stuff on the debugger. So we can write that we have passed the packet to the lower layer successfully, and we can write, for example, all the content of the packet on the debug. Okay? This is just to check what we have put inside the packet. If everything goes fine, we should get this event back from the radio stack, okay? And we can check if the packet was successfully transmitted. Since we have also requested the acknowledgement, we can check if the packet was ACT. So we can call this command, which is already given us by the TinyOS operating system, and we can check whether the message was ACT or not. So if an acknowledgement was received or not. Look at what we do. So if the acknowledgement was received, then we say, okay, we have received an ACK, and we will stop the timer, meaning that we do not want to transmit other requests. Otherwise, if the packet was not acknowledged, we will write that we had not received an acknowledged, and we will try to send another request. Okay, so that's what happens basically. This is for the transmitter side. Okay, it should be clear. We start a timer. When the timer fires, we put the data in the packet, we transmit it to node 2, and then we wait for the acknowledgement. If the acknowledgement arrives, okay, good. If it doesn't arrive, then we have to start another request. That's it. Let's see what happens on the receiver side, so on node 2. Well, the receiver side will run the same code. Okay, since in Tossim we have only one simulation code to be run, so again node 2 will start from the boot.boot event, we'll call the split control, we'll turn on its radio. Then, since if the radio is turned on correctly, node 2 will check this statement. So we'll check if the TOS node ID is equal to 1. Since we are on node 2, this will be false. So node 2 will not start any timer, okay, will just stay there and be ready to receive messages. Whenever a message is received, if you remember, the operating system triggers the receive event, which is this one. And in the receive event, we have to manage the packet that we have received, basically. So this code will be basically run by both node 1 and node 2 upon packet reception. So whenever a message arrives, we get the message, we write a bunch of stuff on the debugger. For example, we write what is the source address of the packet, what was the destination address, what was inside the packet. So we write the 3 fields of the message, message type, message ID, and message value. And then we check if the message contained as message type a request. It means that we need to answer with a response, okay? So we will call the send response function. So since it's node 1 which is transmitting requests, only node 2 will receive this request and only node 2 will transmit back a response to node 1. Let's see what's inside the response. So what we should do in the response? Well, we should create a new packet, put the value response inside the message type field, sense something from the sensor, and put the data that we have sensed into the value field of the packet, basically. So let's see what happens here. So in the response, what we actually do is just to call the read function, which basically triggers the measurement of, so the sampling of a measurement on the sensor. And whenever the measurement is performed, we will have a read done event in response. So in the read done event, which is here, the read done will contain the data coming from the sensor. So what we have to do is to create a new message here. The message type will be response. We will have the ID, which is the same that we have received from the request. And in the message value field, we will put the data that we have read from the sensor. We want to acknowledge this packet, so again we will call the packet acknowledgement function for request an acknowledgement on this packet, and then we will send the packet back to node 1. So the first parameter here is the destination address, this time is node 1. So we will transmit this message, again we will write, if we want, everything on the debug, so what is the content of the packet that we are trying to send, and that's it basically. Whenever the send operation finishes, we will have a send done event, which is the same we have seen before. So if the send done was successful and the packet acknowledgement was acked, then we will basically write that the ack was received. Now node 2 can call this millitimer.stop. It will not create any error since the timer was never started. So even if we stop it, it will not create any error. We could also do something like this here, if you want to be more correct, and say, let me switch to Italian, and say basically if toss node ID equal to 1, then we stop the timer. Okay, since it's only node 1 that has started the timer. But that's not, we can also avoid to do that. Basically, it will work. So this is the source code. I hope it's clear. Have you got any question on the source code? I know I was kind of quick, but if you look it back later, it's kind of simple. Let's just see a very simple thing on on the configuration. So when we wire things together, the only thing that you have not seen so far is how to connect a sensor to your node, and in this case we will use this fake sensor C component, which is again actually here in the folder. And this fake sensor, basically, when you call the read command on this fake sensor, it will basically start a timer, and after 10 milliseconds it will give you back a random number. Okay, so this component is basically a sensor which emulates random data. Okay, you call it, and after 10 milliseconds it retrieves back a random value. If you want to modify this in order to give meaningful data, well, you can try to modify the script, or you can create another component and modify the configuration by passing here not fake sensor C, but the component that you create. Okay, so you can leave all the configuration as it is, but you just detach the fake sensor and you attach the one that you have created. Okay, that's the purpose of having a configuration like this with wirings, that you can remove one component and attach another one, as long as it provides the same interface. Okay, so let's see how to simulate this. Okay. As I told you, if we want to use Tossim, we need to specify a topology. And in this case, the topology, of course, is basically formed by only two nodes, node 1 and node 2, and they need to be connected by links. One link from node 1 to node 2, and one link from node 2 to node 1. How do we specify this? Well, there's a file called topology.txt in your folder. You can display it. And that's exactly how it looks like. So it's basically two lines of code. The first line specifies that we have a link from node 1 to node 2 with a specific received signal strength of -60 dBm, which is a good value. And the second line specifies that we have a backward link from node 2 to node 1 with the same signal strength. So in this case, it's a symmetric topology, meaning that the let's say propagation pattern between the two nodes is exactly the same. So you can specify a topology just by modifying this file here. And finally, let's see how the actual simulation is put in place. It's the run simulation script.py file, which is a Python file which specifies how the simulation should be run. Okay, don't be scared about this file. Again, as we have already seen in many other things, you will just have to use this. Okay, you don't have actually to memorize it or understand in detail how it works. You just have to use it and maybe change a little bit here and there to obtain the specified behavior. So the idea is that you load a topology file and a noise file, as I have explained to you before. Then you perform, let's say, something here, which is basically initializing the max simulation and the radio environment. The interesting things are here. So all the debug channels must be specified here. So here, for example, I'm using a variable out, which can be either a file, text file, simulation out file, or the standard output, meaning the screen of the terminal. And what I'm doing, basically, I'm linking all the channels, the debug channels in my code, init, boot, radio, and so on and so forth, to the same output. Okay. So since the output is the terminal, the standard output, all the debug statements will be written on our terminal. If you want to modify this, you have to specify different files, for example, and then passing these different files here. In this way, you can specify where to write different debug statements. Then another important part is where you create nodes. So what you actually do, you basically go inside the topology and you, for example, get node 1 and specify what is the instant at which each node should be turned on. Okay. So for example, in this case, node 1 will be turned on at time 0, meaning at the very beginning of the simulation, while node 2 will be booted after 1 second. Okay. So by modifying this, you can have different scenarios in which either your nodes start all together at the same instant, or you can specify different booting instant. And this can, of course, make your application behave in different ways. Okay? For example, if the two nodes start at the same instant, when we transmit the first request, we will already receive an acknowledgement. While if the second node will start after, I don't know, 100 seconds, then the first node will transmit 100 requests before we can actually get an acknowledgement. Then we have some other bunch of lines for creating the radio channels and so on and so forth. Well, this is basically code that you can reuse as it is. Now let's see how to simulate this. So generally you open a terminal, you go in the folder, so here IoT examples, no, not download, desktop, IoT examples, TinyOS, Sendak, and then what we have to do is to compile for simulation, which is make Mika's sim. We'll get a bunch of lines here. So if everything goes in the proper way, you should see something like this: successfully built TinyOS and Tossim library. That means that your application was compiled correctly for simulation. And then, if you want to run the simulation, you just run the Python script that we have just seen. So you type Python run simulation script.py. Okay? So if you run it, you have basically that your simulation executes, and you can see what happens. So, oops, I went too far basically. Let me just try to do something here. In the Python script, you can also specify for how long running the simulation, okay, in terms of events. Let me just put 10 events maybe. Okay. So now I've requested the Python script to perform a very small simulation in time. Okay. So what happens basically is that node 1 boots. Okay. Node 1 turns on the radio, and then node 1 starts sending periodical requests. and then the simulation finishes because I have set a very short amount of time to be simulated. So let me just increase this to 100, for example. You should see. Oops. Okay. So let's see what happens. So node 1 turns on, application boot, turns on the radio, start transmitting periodical requests. The first one is transmitting at this time, in simulation time, and we are trying to transmit this packet, okay? So message type is a request, message ID is 0 and value is 0. The packet is sent, but the acknowledge was not received. Why? Well, because node 2 is not booted, okay? Then the timer fires again. Node 1 will try to send a request to node 2 at time 800 milliseconds. Now, this is the second time we tried to transmit a packet, so the counter was incremented now. The first one was 0, now it's 1. But again, the packet was not received. Okay? So we have to wait basically. Where is it? The first second. Okay, sorry. It's still too slow because we have set node 2 to wake up at first second, but we didn't reach the first second in the simulation. We are still at 0.87 milliseconds. So let's increase this maybe to 500. Okay. Now should be okay. So if we increase it a little bit, now we can see that node 2 was turned on, and we see that node 2 receives a message at this time. So node 2 at this point can create its own packet and transmit it back to node 1. So message type is 2, this is a response, and the value is 245. This is the random value that we got from the sensor. At this point, node 1 receives the message, so it stops its timer basically, and node 2 gets the acknowledgement back from node 1, and the simulation finishes because there are no more events in this simulation. So this example gives you a starting point to basically create a very simple application in which you have radio communication between nodes, you have sensor readings, you have acknowledgement in packets, and so on and so forth. Okay, this gives you the basis basically. Any question? No? So my suggestion is play with this a little bit in order to understand how it works. Okay, this is very useful, especially when you are creating your projects. Okay, so when you have to debug whether your application is running or not, using this kind of framework is very useful. Now we have a couple of things to see. So the first one is this. We have already talked about what happens when data is collected by a sensor network. Okay. So you have to imagine that the sensor network is getting the data, and this data has to be delivered somewhere. For example, you want to put it on ThinkSpeak, okay? So you want this data to eventually go into a database. That means that the data that you collect from the sensor network at a certain point must be delivered somehow to a gateway or to a database that then collects this data and on which you can operate. How do we simulate this operation? So how do we simulate that the data which is generated in our simulation can be transferred to a gateway? Well, hopefully we can do this in Tossim. And in fact, this is possible. We will see now different ways of doing this, okay? The first way of doing this that we will see is by using the so-called Tossim Live, which is an add-on to Tossim which permits to read data coming from a simulation. The second way of doing this is by using Kuja and Node-RED, which closes then our discussion. So Tossim Live is this add-on for Tossim, and basically what it does, it creates a virtual serial port between any program on your PC and the simulation that you are running with Tossim. So it's actually like attaching your simulation through a virtual cable to your PC and then having a program which is actually reading this data from the simulation. Okay, let's say from an overall perspective, is really like having your sensor network grounded to your PC somehow. Okay, so that you can deliver data from the sensor network to your PC. There's an example on how to do this. In particular, the example will use a Java program which is reading data coming from a TinyOS simulation. Okay. Again, don't be scared by the different languages that we are looking at in these lectures, because the source code is basically very, very minimal, so you just need to modify here and there the application in order to get it running. Okay, so you are not requested to learn the complete set of Java syntax, for example, or how to use it. So if you look in your folder of TinyOS examples, you should have a Tossim Live folder, okay? And this contains actually the code. Sorry for this Larson, which is maybe if I move here it would be better. Yeah. So no. There's no way to lower the volume. Okay. So, so if you look at the Tossim Live application, this is quite straightforward. So it's basically an application that periodically transmits a packet to a PC. Okay. So we are not talking about mode-to-mode radio communication here. We are talking about mode-to-PC communication. Okay. And this communication is performed through the so-called serial active message, which is a TinyOS module completely similar to the active messages that we have seen for radio communication, but that can be used for mode to PC communication. So, for example, if we look quickly at the source code here, you will have this serial active message component used instead of the traditional active message. And if we look at the implementation, it's here. What the application does, well, it starts a timer, and each time the timer fires, it transmits a message over this serial communication link, and in this packet we have basically a counter which is incremented. So we have a message with just one field, which is a counter, and each time we transmit a message, the counter is incremented. What we see on the PC is the value of the counter. So we have a Java application that connects to the simulation, and each time one of these messages is transmitted, the value of the counter is displayed from the Java application. Okay? If you want to dig into the Java source code, you can look here, testserial.java. Here you have basically the source code that shows how to connect to the simulation, and basically what we are interested to is this one. So it's how to receive a message and how to print basically here the counter which is inside the message itself. There's a README file in this folder with the instruction on how to run the simulation. Okay, so you can follow this in order to run it. The differences between simple simulation is that when you want to compile for Tossim Live, you have to use the keywords make z sim minus sf. This minus sf stands for serial forwarder and informs the Tossim simulation that there will be another process that will intercept the messages basically. So you can run it. Takes a little bit. Okay, and then you have to open these two additional programs. The first one is the serial forwarder. Let's open a new tab. So the first one is the serial forwarder, which is a simple graphical application that shows the number of messages that are going from your simulation to the process which is actually listening. And the second one is the actual Java application that reads these messages. So if you run it like this, nothing will be shown because we didn't start the simulation yet. If we start the simulation here, running Python run simulation script, this simulation will send one packet each time the timer fires, and on the other side we will see the Java program which is actually getting these messages and showing the sequence number which is contained in this message. So this is very important and powerful because on one hand we have a TinyOS simulation of a sensor network which is doing something, and on the other hand we have a Java program, but it could also be a C or a C++ program. That means that you can simulate the sensor network doing something, transmit the data out of the sensor network to the Java program, and then the Java program can do something else. For example, put the data on ThinkSpeak, okay? Or processing the data, or storing the data into a local database, and so on and so forth. So this gives you two building blocks for creating, let's say, an Internet of Things application prototype. Now, you should be quite happy for this, but also a little bit disappointed from the fact that we are using only the terminal, okay? Come on, we are in 2016, we would like to have at least a graphical interface, right? Hopefully we can use Kuja, which is a graphical simulator, plus Node-RED, which has these nice blocks that can be drag and dropped inside, to do exactly the same things as we have seen here. Okay, so simulate a TinyOS application inside Kuja and connect Node-RED to Kuja to get the data out of the simulation. And that's very, very easy to do. How we do it? Well, first of all, let me start Node-RED here. And let me open Kuja. I can close this. I can stop this. So let me open Kuja. Okay. So I will create a new simulation. This time I just need one node, okay, because it's only one node which is transmitting data. And remember that if we want to simulate a TinyOS application in Kuja, we need to use a sky mode, which is basically a Telos B mode. I will load the Tossim live executable compiled for Telos B, so compiled with make Telos B, as we did last time. I will create only one node. It's here, okay. Let me just put 100% speed limit. And then let me open Node-RED so I can show you how we can connect the two processes. Remember that you have to open the browser and go to localhost at port 1880 here. Okay, so I've written a flow that you can import. You can find it here in TinyOS supporting files, TinyOS Node-RED. So you can open this file here and copy this, okay, this code, and then importing it into Node-RED. So let me cancel all this. Come on. So you can click here, import clipboard, and then paste everything here, and this will create the flow that you can use to attach your Node-RED to Kuja. And then remember that you have to press on deploy for deploying in it. So what this flow does, basically, it connects to Kuja through a TCP connection. In order to habilitate this, you have to click on the node and then go here, Mode Tools, and click on Serial Socket Server. So basically this enables a TCP server socket on Kuja, and the client side will be on Node-RED. And by doing this, we can communicate with the two. So we have created the serial socket, the speed limit is set, I start the simulation. So by starting the simulation, it means that this node will try to transmit packets on the serial socket. These packets will be received by the client here, and if I look at the output, where is it? Here. I should see these messages coming in. You see? 25, 26, 27. So these are actually this is actually the value of the counter contained in serial messages coming from the TinyOS simulation. So it's exactly the same I've shown you before with Tossim and Java on the terminal, but in a much nicer environment. So this is graphical. Now from here, you understand that you can attack everything you want. So if you need to take this data and put it on TeamSpeak, you can modify this flow by attaching the flows that we have seen on the first lecture, where we use Node-RED to put data on TeamSpeak and deliver this data directly on the cloud, for example. So we have the visual wireless sensor network simulation on one hand, either in Kuja or in Tossim, data transmission to Node-RED, and then from here you can do whatever you want. Logging into a database, plotting data using some plotting cloud system or whatever you want. Okay, good. This closes this lecture and basically closes also the part on TinyOS. From the next time we will see Contiki and Motrunner, so the other two operating systems. My suggestion is start playing with this right now. I mean, it's as simple as redoing what I did in this lecture, okay? Look at the video that we will put on YouTube and just try to redo this. This basically gives you all the building blocks that you need for the projects, basically. Okay? Good. See you later. Hi.
Well, when you were mentioning about this script, so the timing which you change in Node 2, I wanted to know like what will be the standard time frame for setting in Node 1 and Node 2. Although it depends upon our application, but since it's in very like time is an important factor in IoT, so what will be the standard time frame which is generally used for projects?
As you wish.
No, but you can suggest us it's first time for us, so then we'll.
So you can either make all your sensors start at the same time,
Okay.
but this is not very realistic, right?
Yeah, this is not.
So generally you insert, let's say, couple of seconds of delay between one node turning on and the other one. It could be a couple of seconds, it could be 500 milliseconds, something like this, okay? Think about what's happening in a real application. You actually have to put your nodes and then turn on one by one, okay?
And how big the application need to develop? How big an application?
What do you mean, how big?
Since you said everything is going to be on software, of course, so for like if we want to deliver the project before September, so as Professor said, so how big an application should we go for? Like how much is the complexity in terms of complexity? Because you are showing us the simple examples.
Yeah, it will be comparable to these simple examples.
So, when will we get the list of projects?
I guess in next week. I have already come up with 3 ideas.
Okay.
So I just have to write the description for these ideas, and then I will put everything on.
But we have to write the source code for those, right?
Yeah, for one of those, not all. You have to choose one.
Yeah. No, we have to. I mean, whichever we choose, we have to write the source code for that.
Exactly. Yeah.
So, which one do you prefer, like TinyOS or the remaining two for projects? Like, which is more easy?
I think TinyOS
Because
is
of
gonna be
TinyOS
is gonna be more easy.
TinyOS is easy. Because Zively, you said we're gonna need some in initial classes. We're gonna need some username, password, and all. So it's like
Yeah, I mean, don't worry about this. It's gonna be much simpler than what you are thinking.
because seeing the script, it's,
As I said, you don't have to become fully an expert on this. You just need to understand what the code is doing and modify it in the proper ways in order to.
because those who are from telecom, it's like new programming is
Yeah, I understand. But it's not the first time that we do this, so we know
Yeah.
exactly how students react. Okay.
Thank you.
But hi.
Are you? I always have this error. How do I?
Could not read from the boot medium. It seems that there's something wrong in how you imported this,
Well, I just follow the instructions.
and it's not working. That's strange. Can I power up? So these are all the same. Can I create a new one? Yes, yes. Type mix. Ubuntu properties. Yeah. Name Ubuntu 3. But I don't want to create one. I actually want to import the appliance. So it goes like this. Where is the file? You're good. I like your way of putting folders. I'm not as ordered as you are. Next. You didn't do anything then, right? It's really strange. Can I, so if I run this, it will give. That's so strange. No button on video. Have you searched a little bit?
Yeah, I did.
here
I
and
did. I tried to Google it, and then somewhere they gave me solutions that said I need to change the this boot order, and I changed the boot order targets, the optical and floppy, but then it didn't work. I think the main problem is in here in the controller ID.
Yeah, so maybe we can try to create a new machine like this and see whether it works if we pass the artist back. Let's see if we can do something like this. Use an existing. Did you already try with this? Let's go on. Yeah, where was it? Here, the masters. So easy to find. This software. All files. Let's see what happens if we use this. It doesn't want. If we use the ones
normale questo?
which are probably
Sono uscito questo.
where can be this
È peggiore. Quanto sono perso? Sotto il legno. Sì,
there's a folding all the virtual machine are stored, but I don't remember where is it. Maybe here, no.
Cioè, secondo te la risposta è aspettare che devi
Oh, what am I doing? Ah, but they are still running. Power off.
Che occhio dolce.
No, però c'è una situazione di caffè.
New.
Ah, quindi questi
Ubuntu.
Cosa di mio interesse?
No.
non sono solo
Let's give it 1 gigabyte. News. Was. Users. This one. Virtual quality.
Quindi come protocolli cosa usiamo alla fine?
sono co-op. Però io vorrei esattamente così questa qua. Quella evidenziata.
It's not very good, but we'll see what happens. It's very strange. I'll try to search a little bit and see what I can find a solution. Okay.
Scusi, una cosa.
Sì.
Il codice che abbiamo visto prima,
Sì,
quello del send act
sì.
questa posta di questo task qui è corretta. La prima domanda è: questo packet acknowledgement was hacked è bloccante? Cioè si ferma per vedere se entro un certo tempo arriva l'hack?
No, perché dunque, com'è che funziona? Sì, non mi ricordo.
Cioè,
Allora,
questo qua comunque a me, cioè questa cosa qua viene chiamata non appena il pacchetto esce, giusto, dalla
sì,
mia radio.
sì. E no, un attimo. Sì, è così. Questa cosa qua arriva appena il pacchetto esce e o meglio, se qui è un po' particolare la cosa. Leggetevi come funziona questa interfaccia, adesso non mi ricordo benissimo, ma dovrebbe ritornare immediatamente se il pacchetto è stato, cioè, se è stato ricevuto l'acknowledgement o meno, perché quando il pacchetto viene ricevuto dal destinatario, se il pacchetto era stato marcato come da fare l'acknowledgement, TinyOS manda automaticamente un acknowledgement indietro prima che il pacchetto sostanzialmente venga ricevuto e portato su ai livelli superiori. Quindi sostanzialmente qua voi vi aspettate già che arrivi l'acknowledgement senza aver scritto niente sul ricevitore. È una cosa che viene gestita automaticamente dal sistema operativo, quindi rimane ai livelli.
Cioè come fa a fare? Nel senso, io questo qua qui ci arriva non appena esce dalla radio, non quando arriva dall'altra parte. E quindi mi chiedo, cioè se non aspetto neanche un po' col time.
È sicuramente dentro qua,
okay.
però voi lo sviluppatore non lo usa questa cosa qua. Ci sarà sicuramente un piccolo delay, ma sarà così breve che per voi è ininfluente.
Questa post qui invece, nel caso in cui non abbia ricevuto l'acknowledgement,
Sì.
è giusto fare la post, dato che abbiamo fatto partire il timer in modo periodico? Nel senso, se non lo stoppo,
Sì,
riparte.
sì, esatto. Sì.
Senza dover
Sì. Sì, i task come funzionano? Che praticamente, visto che il timer posta il task, la regola dei task è se il task è già in coda non viene ripostato.
quindi non è che ne vengono postate istanze multiple, quindi comunque in ogni caso va bene anche non metterlo, perché se arrivate qua la richiesta è stata già inviata, quindi il task è uscito dalla coda, quindi ne verrà messo un altro.
Poi in Cuja, quando facciamo
Sì.
quel lavoro qui di questa roba qua del server,
Sì.
lui che cosa si aspetta di trovare nel codice? Cioè qual è la parte che fa il collegamento effettivamente tra questa roba qui e quello che è fatto nel codice? Il fatto che utilizziamo
Il
quel
serial
componente-
active message, il serial active message,
che lui va a
sì.
cercare quel componente all'interno della nostra applicazione.
Ma in realtà adesso noi questo Kuja lo stiamo usando in maniera un po' anomala, perché il serial active message è pensato per Tossim Live, però magicamente funziona bene anche per Kuja, quindi io sono riuscito a trovare, penso che non
l'hanno fatto apposta.
non l'hanno fatto, nel senso sono riuscito a in questo modo collegare le cose. L'utilizzo del serial active message è fatto per Tossim Live, però visto che la comunicazione seriale tipicamente è implementata sempre nello stesso modo, questa cosa qua funziona. Quindi se voi riutilizzate nella vostra applicazione il serial active message esattamente come è utilizzato nell'esempio, dovrebbe funzionare anche qui.
Mentre quando noi facciamo un'applicazione in TinyOS,
Sì.
è possibile definire una variabile?
Sì? Non ti guardo ma
Sì,
perché sto
ok.
spegnendo.
No. Stavo pensando come formulare la domanda. Io voglio avere una variabile all'interno del codice e assegno un valore a quella variabile nel momento in cui compilo con make.
Sì, si può. Nel
Posso farlo?
makefile si fa. Nel makefile,
Nel
questo si fa di solito per specificare per esempio la frequenza a cui devono lavorare i nodi o la potenza di trasmissione. Nel makefile si specificano dei flag, si chiamano sostanzialmente, che sono delle variabili che hanno come in C, esattamente.
ok.
Ci sono due tipi, mi sembra D flag e IP flag. Adesso non mi ricordo bene la
li abbiamo
differenza
già
fra le
sentiti,
due
ma anche
cose.
io.
Comunque se cerchi, forse ci sono anche già degli esempi. Se tu guardi nelle applicazioni di TinyOS, quelle di esempio, se guardi i makefile dei differenti esempi, troverai in alcuni makefile dei flag, e quei flag lì ti danno il valore della variabile da dare a compile time sostanzialmente.
Quindi se io tipo voglio creare, non so, 50 nodi e avere un attributo su ogni nodo che mi dice ad esempio la stanza in cui il nodo si trova, con un ID. Posso fare anche una cosa come questa, specificando. Cioè o lo faccio con l'if come abbiamo visto adesso, durante il boot, dico magari nodi con ID minore di 20 sono nella stanza 1, oppure posso farlo quindi poi in Kuja abbiamo detto che non possiamo avere libertà di settare la potenza della radio, queste cose qua.
No, in Kuja si può anche qui. Allora, Kuja non è
fatto per TinyOS,
o meglio, Kuja non è un po' in beta, diciamo, quindi alcune cose non funzionano. Ce l'hai aperto?
Sì.
Ci sono delle primitive per settare la dimensione del raggio di comunicazione.
Perché infatti ho provato a fare un'applicazione mia, ma viene minuscolo, cioè devo zoomare a 10.000.
Sì, però quando guarda, clicca sul nodo Mod Tools, no, non è qua, forse è View Radio Environment, Radio Environment. Change Transmission Ranges. Ok, questo si può fare più grande e più piccolo sostanzialmente.
Ok, perfetto.
Quindi così si modificano.
E così simulo,
Allora,
diciamo, sia la potenza che il problema dell'ambiente. È meno.
Esattamente. E poi c'è anche un altro parametro che è il TX-RX ratio, che è una percentuale di successo sulle
quindi questo qua serve più a
trasmissioni.
simulare il noise,
Anche lì si può simulare un po' di roba.
Ok, va bene.
Quello dovrebbe funzionare indipendentemente dal codice sorgente. sia con TinyOS, con codice sorgente TinyOS che con codice sorgente continuo.
Ok, va bene. Poi noi vedremo anche come implementare coop su TinyOS.
No, ci fermeremo semplicemente, cioè vi farò semplicemente vedere come utilizzare.
Cioè, sì, no, non dico implementare, dico utilizzare coop per mandare un messaggio, queste cose qui lo facciamo?
No,
Niente?
no. Però è già sia per TinyOS che per Contigo dovrebbe già essere implementato. Quindi si
Quindi,
tratta
sì.
semplicemente di utilizzarlo.
Ok, va bene.
Perché voi dovete usare coop.
No, stavamo ancora decidendo.
Sì,
Stiamo cercando di capire cosa
qualche
possiamo fare,
studente
cosa
l'ha
no.
già usato in passato, quindi di sicuro si può fare.
Ok. Ma in coop, io ho guardato adesso un pochino, ho provato a informarmi da solo. Ho visto che ci sono tipo delle observation per poter dire quando cambia questa cosa mandami un
Devo
messaggio.
spegnere.
Sì.
Vabbè, ci sarà ci sarà